Hi everyone, my name is Krina Mehta. In this video, I will provide an introduction to physiologically based pharmacokinetic modeling approaches. So as this name suggests, physiologically based pharmacokinetic models are the mathematical models that aims to integrate the known knowledge about the physiological processes for the particular species of interest with the physicochemical and as well as ADME and any other attributes known about the compound in question in order to predict or simulate pharmacokinetic properties. As this definition suggests, these PBPK models are mainly simulations based. It could involve estimation or more likely optimization of few parameters, but other than that, it's mainly simulations based. These models are quite similar to our traditional one or two compartment models in structure. However, it involves organs as the compartments, and the blood flow rates decide basically the drug transfer from one compartment to another compartment. So these compartmental PK models are so-called top-down modeling approach, where you start by getting your system, such as your PK dataset, and then you try to describe this system by breaking down into pieces, like you describe your absorption model, you describe your structural model, you describe your elimination portion, and you incorporate your covariates, all this to try to come up with a best explanation of your observed data using the model. On the other side, the PBPK and most QSP models are an example of so-called bottom-up approach. In this bottom-up approach, you gather all these puzzle pieces together, such as you gather your physiological information, your physical-chemical attributes, your ADME properties, and then you assemble them together to make up your whole system, such as to describe the PK observations. Now, since in the PBPK models we have organs as our compartments, they can be used to simulate concentration time profiles in any tissue of interest. So this could be very useful in understanding direct effect of the drug at the site of action, because you have your concentration at the site of action. So far, the general areas where PBPK models have been assessed and been used are drug-drug interactions, to understand enzymes or transporter effects, to understand effect of certain organ impairment, quite a bit in the formulation developments, specifically the oral formulation development, and the dose adjustments for the special populations, such as pediatric or pregnancy. They've been used quite a bit into the environmental toxicology area, not so much in the drug safety assessments as of yet. So they're well suited to incorporate in vitro data, and by conducting in vitro to in vivo extrapolations, you can get your PK estimates very early in the drug development, and this could be used to optimize the in vivo trials and optimize and reduce the in vivo trials. They have great extrapolation abilities from one species to another, and one population to another, as well as one dose to another. So to name a few disadvantages, PBPK models require a lot of data or the information about your compound as well as the physiology. If you're trying to model this PBPK models from scratch in the software such as non-MEM or R or Berkeley Madonna, they can be complicated. So, but luckily these days we have software such as the PKSim as an open source software where you have these models built in, and it's sort of click and choose. So here is a standard schematic of a whole body PBPK model. Each major organ is modeled as a compartment, and your drug transfer is based on the blood flows. In each organ, you have the arterial blood flow coming in and the venous blood flow coming out. Please note that the lungs is the other way around. It's easy to forget. So for the intestine, you could have the gut extraction, liver and kidney are also eliminating organs. If you have an oral drug, it goes into the stomach through intestine, and through the portal vein it goes to the systemic circulation. So you have that movement here. And you could also include the enterohepatic recirculation from the gallbladder to the intestine. Now each organ can be subdivided into different sub compartments as well. So this is the standard PBPK model that is built into the PKSim software. So for the purpose of understanding the theory, we want to simplify the subdivision of each organ. So in general, the organ you consider the blood vessels, so the vascular portion of the tissue, and tissue mass basically. Now, there are two main types of tissue parameterization known as the perfusion limited kinetics or the permeability limited kinetics to describe your drug kinetics within the organ. So we are going to understand what are those two types in the upcoming slides. And the third one is for if you have the protein or the large molecule, you want to include some additional processes as well. And we're going to briefly describe the protein model in the upcoming slide as well. So for a simple rule for the small and lipophilic drugs, perfusion limited models for most organs are good enough. So the large or hydrophilic drugs may need some organs to be permeability limited to describe their pharmacokinetic very well. So in GastroPlus, there is an option to switch between perfusion and permeability limited models, and it's up to the user to decide that. And for the PKSim, it's more like a built-in where it automatically switches based on your physicochemical and the physiological properties. So we'll discuss that in the upcoming slide as well. So the perfusion, or also known as the blood flow limited kinetics, is that here you have your venous portion of the tissue and your tissue mass basically, and the assumption here is that there is no resistance between this vascular and the tissue portions, and the drug reaches a steady state very quickly. So at steady state, the total drug concentration in the tissue is at equilibrium with the total drug concentration in the blood portion. And this ratio of total drug concentration in the tissue to the total drug concentration in the vascular portion is called partition coefficients. So here we are talking about total drug concentration. But when the total drug concentration is at equilibrium, your free drug is basically equal. Free drug concentration is basically equal between the vascular and the tissue portion. So here basically your drug kinetics is limited by the blood flow rate. Hence it's called blood flow limited kinetics. And it can be described by a simple first order kinetics. Here you have the blood flow rate and your concentration in the arterial blood minus the concentration in the venous blood. So simple enough. Now on to the permeability or membrane limited kinetics. Here you have an extra compartment known as the extracellular space. Here there is some resistance between intracellular and vascular portion of the tissue, and your cell membrane acts as the diffusional barrier. Here your assumption is still that at the steady state, total drug is in equilibrium between the vascular and the tissue portion. However, time to reach this steady state is limited by the permeability of this cell membrane. So in the equations, you need an extra parameter called permeability surface area product to describe your kinetics, and you need two separate differential equations to describe your kinetics into that particular compartment. So that's about the permeability limited tissue model. If you would like to learn more about this permeability versus perfusion limited models, this is a very good resource to read. So now, how is this model in the PKSIM? In the PKSIM, there's just general two settings available. You can use either model for the small molecules, or you can uncheck that small molecule button and it will activate the protein models. So when your small molecule is selected, the PKSIM will automatically define which tissue is the perfusion limited and which one will be the permeability limited based on the permeability surface area product. And this permeability surface area product parameter is nothing but the multiplication of the cellular permeability and the surface area of that particular organ. So it's simple here. When your permeability and surface area product is greater than the blood flow of that particular organ, here the rate limitation will be the blood flow. So it will be the perfusion limited model. And when you have it other way around, where the permeability surface area product is less than the blood flow, the cellular permeability will be the rate limiting factor, and then it will become the permeability limited model. So how it works in the PKSIM is basically the cellular permeability is estimated based on the physicochemical properties that you input. And of course, the surface area of each organ is already known as a physiological property and it's built into the model based on the species you select. So it just calculates the permeability surface area product, and you have your blood flow rate, and it determines which one will be the rate limiting factor, but it doesn't really show you all that information. It does all that calculation and includes it in your model behind the scene. Now, a little bit about the protein model. When your small molecule box will be unchecked in the PKSIM, the protein model becomes active, and it takes into account the drug movement between the interstitial space, lymph flow, endosomal clearance, and it also takes into account FCR and mediated recycling, all that information. But for the purpose of these lectures, we are not going deeper into the protein models. But if you are interested, this is a very good paper that was recently published by the PKSM team going deeper into this protein models. That was all about the PKSM. But if you're trying to, build your PBPK model from scratch into some of the programming software such as NonMem, R, Berkeley Madonna, what you can do is to lump some of the organs together based on the blood flow rates to simplify the model. Here, this is an example where you have mainly three organs: fat, liver, and lung. And then the slowly perfused organs are the fat, skin, muscles, and bones. And the richly perfused tissues are the rest of the organs. So there are some basic rules about slowly perfused organs versus which one to consider the richly perfused tissues or organs. In general, fat, skin, muscles, and bone are considered slowly perfused because of the blood flow rate. Most of the time, brain is considered a richly perfused organ, but sometimes it can be also modeled as a slowly perfused organ because of the small blood volume fraction and, of course, the tight blood-brain barrier. So it depends on the type of the model you're trying to build, and it depends on project to project which compartment or organs are important to particular project, and depending on that, the structural model can be determined. PBPK models, the parameters, the common parameters can be divided into two main groups. Physiological parameters, which are the species specific, which would include the organ volume, surface areas, tissue compositions, blood flow rates, protein abundance, all that. And on the other side, the drug specific parameters, you need mainly the distribution related parameters and disposition related parameters. And of course, you need the absorption related parameters too if you're considering the extra vascular absorption. So for the partition coefficients and the permeability calculations, in the older days, they used to be measured by the experimental methods in the animals, where they do the experiments and extract those organs from the animals, and then estimate the ratio of the total drug concentration in certain tissue to the total drug concentration in the vascular portion. But luckily, we have these days we have very good in silico models available, such as Pauline and Till, Schmidt, and the most commonly used and most advanced model is the Rogers and Rowland method to calculate the partition coefficients. And for this prediction models, basically you need some of the basic physicochemical properties. Other than the distribution parameters, you need your metabolism and elimination rates and absorption rates, and any other parameters that you are trying to incorporate, such as like transporter effects or enzyme effects and all that. So this is it for this first video. And here are some of the references that you can look into, and I'll see you at the next lecture. Thank you so much.